Good evening, everyone. This is 11th talk of the day. So I guess the safest approach is to tell you everything on the first slide, the main results, the main story, and then you can doze off and just come back to me when I acknowledge the group and collaborators. So the title of the talk is Full Counting Statistics in Quantum Thermodynamics, and as an example, I will talk about a model for an absorption refrigerator at strong coupling. So we are interested in heat exchange problems. We have a quantum system. I'm not doing anything. We are interested in heat exchange problems where we have a quantum system and nanoscale systems in contact with an environment, and there is an exchange of heat. We are not going to investigate time-dependent Hamiltonians. We are interested in average energy currents, but we are going to use the full counting statistics approach. So you may think, you're overdoing it, but in fact, calculating the full probability distribution function for heat exchange is easier in a sense because the formalism is very similar to reduced density matrix approaches, so it's quite convenient. And of course, you get a lot more than just the average energy current. You get noise. You can convince yourself that you satisfy fluctuation, heat exchange fluctuation relation. Therefore, you are working under the umbrella of the second law of thermodynamics. You satisfy the second law, and so on. So the example will be an absorption refrigerator at strong coupling. So this is a model that I'm not going to focus on. What is it? Well, it's an absorption refrigerator that has been investigated a lot. There is a nice review by Ronnie and others. The objective is to cool down, to extract energy from the cold bath and to dump it into the hot bath. And you need to do some work, and the way it's done here is actually by including an additional thermal heat bath, which is just very hot. So we refer to it as a work reservoir. So what you would like to cool down this cold bath, dump the energy to this one. And this is a working fluid, a 3-level system. And there were many studies based on a weak system bath coupling approximation. So all these 3 reservoirs are weakly coupled to the bath. Something about this. The 3 reservoirs are weakly coupled to the system. And therefore, every transition is induced individually by a separate bath. So that's the main design principle here, that each transition going up or down, comes from a separate bath. And what you would like to enhance is a process that is indicated here, taking energy from the cold bath and then additionally from the work reservoir and dumping it into the hot bath. And again, the main design principle is based on the weak coupling assumption that they are individual transitions. You don't mix them up. It's going to make your life more complicated. In contrast, I'm going to focus on this model where actually the working fluid is just made of a qubit, just a 2-level system. And again, the same objective. We would like to extract energy from the cold bath. And we will be able to achieve that using strong coupling, as I will explain to you. So indeed, the main ingredient here is going to be that rather than a sequential process, we are going to realize a cooperative energy transport process, and that's this strange error where cooperatively these 3 reservoirs are going to work together so as we take some energy from here, from the work, and dump it into the hole. What we're going to describe today is organized into 2 publications. The first one is actually still in preparation. So that's this publication will focus on the method. The first author, Chava Friedman, she's here in the audience. She's a graduate student in my group. The application, the qubit absorption refrigerator, is already on the archive, and the first author, Anki Mu, is a 4th-year undergrad in the group. But I should mention that actually the theory behind the method we have been working on that for a while. It's actually very much related, not sure. It's actually very much related to, okay, let's get in there. To the talk by Chow this morning. So we have been working for a while on heat transport problems. So just 2-terminal energy transport problem from the hot bath to the cold one, mediated by qubit. And we were looking, we were contrasting these two situations, a sequential transport resonance, sequential transport process, and a cooperative energy transport process. So yeah, focusing on these systems in previous publications. I also want to mention that we have had also a recent project on squeezed bath. We didn't use this, or we did not invoke this idea of passivity. It was more traditional. Yeah, so it was about heat engines where we are going to extract energy from a squeezed thermal bath and gain some work, which is used to drive electrons against the chemical potential difference. And yeah, we derived a bound for efficiency, which depends on the squeezing parameter. Yeah. Should I copy my presentation to a different computer? Do you think it's my computer or the...
There's one thing you could do. See if you can lower the resolution. Maybe it could be a resolution mismatch.
So yeah, I could mention the... I also have it on this key. I can copy it if you suspect it's my computer.
No, I don't think it's the computer. It could just be a mismatch in there. Sometimes this happens, but I cannot get the somewhere where it tells me what the resolution is. With the color.
You have it on this key?
Yeah, I do. Yeah. Do you want to give it another try? Or to...
It's on, but I don't know
Whether it will
stay.
yeah, so... so
Just sit here.
okay.
It's because I observe it.
So yeah, I'm not going to discuss this problem about the squeezed thermal bath. As I've said, yeah, so I guess we need to copy it. We didn't invoke the idea of passivity. It was a two-level system here, and we were able to define an effective temperature which already takes into account the squeezing parameter. And therefore, I think we eventually get an efficiency bound that is in agreement with your work, but it's specific for two-state system. Well, definitely we didn't get the efficiency bound to get above 1. We were bounded by 1. No, we did. I can show you in the paper. It is limited by 1 also analytically, but the trick here, you could say, I would say maybe the tricks that we do is that our two-level system, the temperature is defined already for the subsystem. It's not a general study, what we did. So it's a 4. But yeah, we can, it's not the main story here, so we could, yeah, this is not the one, it's a 4.
I don't know where. Full complex.
So, how do we?
Oh, it's on the other desktop. So, what? Yes, I think we need to. Here.
I can manage. Yeah, I can manage.
Ah, okay.
So the color scheme is a little bit strange, but okay, it does work. Yeah, so we'll talk about the other paper later. Okay, so finally the introduction, the outline of my talk. I will begin with some definitions, some basic ideas for non-equilibrium statistical mechanics, just to put the definitions in front. I will then present our formalism for full counting statistics. And okay, so what do we have? We have a subsystem with few levels. and V is the operator of the bath that couples to the system, the operator of the full total environment. We are going to consider two cases. We have the actual environment is decomposed into several thermal baths. So one model will be additive in these interaction operators, and the other one will be given the total interaction operator of the bath will be a product of these B's operators of each bath. I'm just for simplicity here assuming that these operators are Hermitian, but in the paper with Chava we went beyond that. Then we are going to describe two applications. Energy transport, very similar to what Chao had in the morning, and three-terminal problem, which is the main application, the quantum absorption refrigerator. Yeah, okay, so just to begin with a brief background, what we need, exchange fluctuation theorems. We are going far from equilibrium, and the nice result here, I should have said it's in steady state. The probability function to transfer an amount of heat Q against the temperature difference is, we do have finite probability for that, but it is exponentially suppressed. And this is, of course, just an example of the general exchange fluctuation relation. This is supposed to be delta S, so that's the entropy change in the process. And again, we have a finite probability to have a negative entropy production, but it's exponentially suppressed. And yesterday in the talk of, in one talk, we have had fluctuation relations for charge transport, very similar. Now, I'm not going to work actually with this probability function. Rather, we are going to always consider what we call the characteristic function, Z. It's just a transform. And this is a so-called, the lambda, the so-called counting parameter. Yeah, so we can translate the fluctuation symmetry to a symmetry relation for Z, a very straightforward result. And furthermore, from the fluctuation symmetry, you can get this equality. And I mention it because from here we can immediately derive the second law. We have this relation, Jensen's inequality for convex functions, where the convex transformation of the mean is always below or equal to the mean after the convex transformation. And this gives us an inequality for, again, it's delta S, the entropy production in the process. So yeah, so if the main point that I want to make is that if this symmetry is satisfied, we know that the second law is good, it's done. Yeah, and there are, of course, nice reviews by people from the audience. Yeah, now why full counting statistics? As I've said, we are generally interested just in the average energy current, but this will give us more information, not just the averages, but furthermore, the average current, but furthermore, we can get the noise, skewness, and as I've said, the fluctuation symmetry. So we are going to focus on Z, which is a transform of the probability for heat exchange Q. And as you can see from this definition, if we take derivatives with respect to I lambda, we get the cumulants. So Z is going to be our main of interest for us, the main objective here. I should also mention something very quickly about the two-time measurement protocol, which was mentioned yesterday in the context of the work fluctuation relation, but it's the same story here. It's sort of the complementary situation where we don't have time-dependent Hamiltonians, so whatever we measure is related to heat exchange. Yeah, so the same question, how do we construct the probability distribution? We are going to define the, we have the Hamilton, let's say we focus on the left Hamiltonian, only the left side. We measure it time 0 at a finite time t, where this is the Heisenberg time evolution. And here at the bottom, and this is a function, the characteristic function for heat exchange, which is of interest for us. It is constructed as follows with the exponent of the counting parameter and the Hamiltonian of the left side at time 0, and the similar structure but at time t, and the expectation value is over the initial condition. And what I'm missing here in between is indeed this two-time measurement protocol, which tells you how do you construct this Z. It comes from same story as we have heard yesterday. You measure at time 0, you allow the system to evolve, you measure it at a later time. So you take this function, you multiply it by the initial condition, you sum over I and j, You do the transform here with respect to lambda and with S, and you get this one. Okay, so that was the introduction, and now more specifically, so this is a general Hamiltonian that we are going to consider, a system, let's say 2 states, but of course it can be more than that, several thermal baths up to n, and very simplistic, as I've said in the paper, we have a more general description, a system operator coupled to an operator coming from the environment. We can count a heat exchange between not only, say, the left side, but between every bath in the system. So one can write a more general expression for the characteristic function. The nice thing about it, and this is what I mentioned at the beginning, is that you can organize it in a language that is totally analogous to the density operator time evolution equation. So you can reorganize this equation as time evolution from the initial condition with this time evolution operators that are just the regular one, but dressed now by the counting fields. So that's the main point here. We are going to, rather than immediately doing the full trace, we are going to take first the trace only over the bath. So we are going to have a counting field dependent reduced density matrix, and we are going to study its dynamics and eventually do the full trace over the system degrees of freedom and achieve Z. So that's indeed the animals that we are now going to consider, and it will eventually give us the full counting statistics. What can we do? Well, we will just open the book and do what everyone does, and we've heard it several times. Let's do just Born-Markov, even the secular approximation later, the very standard weak coupling, system bath coupling approach. And here it's written, rather than with the Lindblad formalism, the Redfield formalism. So this is a Schrödinger representation, and well, let's define some things. EKJ, for example, these are the energies of the subsystem. So this is energy difference, EK minus EJ for the subsystem. As usual, we assume factorized initial conditions. These are transforms of the two times correlation function of the bath operators that is coupled to the system. And in the Redfield formalism, before you do the secular approximation, you get this half Fourier transform positive, and also you have the negatives one. Just the upper limit is going to be from -infinity to 0. So that's a very standard approach, and the only difference from the regular Redfield equation is that we decorate everywhere the 2 times correlation function by this counting parameter, because the time evolution was dressed by this transformation with the counting field. Furthermore, let's make the secular approximation. We are doing all the simplifications that we can make, and we get a simple equation for the population dynamics with just Fourier transform of bath correlation functions. It's a very regular approach. Maybe the formalism is a little bit, too many symbols, but these are the correlation functions, time correlation functions of V, the operator of the bath. And N here is to indicate that there are several reservoirs within my total environment. I haven't yet said anything about that. So I'm going to solve it in steady state, and then this is a unit. So I'm going to sum over it and get the characteristic function, which is, again, the main objective here. It will give me all the cumulants. Okay, let's just focus on the energy current. That's enough, even though it seems like we did a lot to get it. If you use this formalism, this is a very simple dynamic equation. You can organize the energy current in this form. So if I know the dissipator, the counting field dependent dissipator, I should take its derivative with respect to lambda, and I can calculate the energy current in the system. Again, what I should highlight is that all this formalism is just general for a total environmental operator V, which is coupled to my subsystem. And as I've said at the beginning, I'm going to consider 2 cases. These B's are the operators of each bath coupled to the system. So I'm going to have an additive model and a model with this product type interaction. So let's begin with the additive model. Obviously, the 2 times correlation function, the total one, just decomposes to the sum for each bath. What is the meaning of that if you think about the rates? I have transitions between the levels induced by the reservoirs. So I have transitions induced by the left bath, and I have transitions induced by the right bath. So it's a very regular weak coupling approach that we always do, where each bath independently leads to transitions in my system. And here, just to clarify, I'm only doing this counting with respect to the right bath. So I have two dissipators, one coming from the left bath, one coming from the right bath. And this was my general expression for the energy current. I can continue and simplify it. And luckily, I got what everyone is using right away, but we did we did have some efforts to get it, a very standard expression for the energy current. You showed it yesterday. It's just the P dot and Hs. So the additive model gives us the regular results. What about the non-additive model? Well, now the time correlation function is a product of operators coming from the left bath and the right bath. And of course, the rates, the Fourier transform are just convolutions. So maybe that's the first new result of this whole story. Not very surprisingly, but it's quite interesting. So now the rates, all these transitions, they are convolutions, meaning that if I have an excitation or whatever transition between N and J, part of the energy is extracted or given to the right bath, and the rest is given to the left bath. So it's a cooperative process. Sorry. And this is what we refer to as strong coupling. So it's true that we are doing the regular Redfield, Born-Markov secular approach, but we think about this type of interaction as representative of strong coupling, as if there is a more microscopic Hamiltonian that leads actually to this interaction which reflects strong coupling. And I will show it in an example in the next slide. What about the energy current? Again, using this full counting statistics approach, immediately I can gain a closed expression for the energy current in the system. So again, it shows, cooperative, energy transfer processes where part of the energy, I'm in a state J and I'm making a transition. Part of the energy goes to the right side and the rest goes to the left side. And I'm integrating, with this, whatever energy was exchanged with the right side. So that's, of course, a steady state result. As an example, if we have a two-state system, we can calculate the cumulant generating function. Previously, I showed you the average current, but we get in full glory, the cumulant generating function. And this is before we assume either the additive or the non-additive model. It's valid in both cases. These are the rates to go up and down. So again, in the additive model, we will get the regular expression for energy flow in the system, where, we just make sequential transitions between these two levels. And if it's a non-additive model, here is an example of the general expressions that we have had before. Since it's less standard, again, let's focus on it. So I just have two states, P0 and P1. And it's already a steady state situation. So these are the steady state values of the population that I have to calculate separately from the population dynamics. So let's say I'm in this excited state, P1, and I'm going to relax. I can relax by sending part of the energy to the right side and the rest to the left side. You see the overall energy exchange is omega naught. For the overall transition, I had to fall down by omega naught, but I can extract or deliver a continuous amount of energy. So energy exchange is a cooperative process, and that's what we refer to as strong coupling. As an example, just to clarify the fact that this additive and non-additive are not necessarily distinct models, let's take a look at the spin boson model that was indeed considered and discussed in the morning by Chow. So we have the two-state system with omega naught as a gap and delta as the tunneling energy. Nu is the index of the reservoir. So we have several reservoirs, and J is the index of the mode. So these are a collection of harmonic oscillators for each bath, and then just a standard model of the polarization coupled to the displacement. This is obviously an additive model. So the system is coupled additively to each bath. After the Polaron transformation, this is what you get. So now it's a non-additive interaction model. Now it's a system operator, sigma plus or sigma minus, coupled to this animal, and this one, yeah, it's a sum, but it's in the exponent. So obviously you turned an additive model into a non-additive one, a product one, and from here what we are going to do is just the Born-Markov, just the treatment for the dynamic in the regular low-order perturbation theory, but immediately it includes interactions beyond the lowest order in lambda, because it appears in the exponent. So that's why I'm going to refer to this model with this multiplicative interaction as a strong coupling model. Yeah, so now to the examples. The first example is for what we refer to as two-terminal models, where we just transfer energy from hot bath to cold bath. We were interested in this problem for a while, for different reasons. Studies of full counting statistics, for method developments. We were comparing results from different approaches with the idea to indeed understand the validity of different methods. And another motivation coming, I'm in a chemistry department, another motivation was to actually be able to relate to some experimental results concerning molecules. So it's maybe very far-fetched off, but still let me show you what they can do experimentally. This is from the group of David Cahill at the University of Illinois, Urbana-Champaign, and it's a recent experiment, maybe 2 years ago. This green stuff is an alkane molecule with 11 carbon atoms. And it is either chemisorbed or physisorbed to this glass and gold surface. And they study the propagation of energy. So forget about electrons, it's just vibrational energy flow through the system. And indeed, the question that they were addressing was what is the role of the molecule being either physisorbed or chemisorbed on the energy, on the thermal conductance of the system. So it's sort of a similar question about the weak coupling or strong coupling to the environment. How does it influence the transport process? And from a different perspective, this is from the group of Igor Rubtsov, Tulane University. So I don't know if you can see the molecule. It's here. So there are, again, several carbon atoms, n of them, let's say 10. And they are asking actually very similar questions regarding heat flow, vibrational energy flow in the system. But now it's an ultra-fast experiment, pump probe experiment. So they excite what they call a tag mode. They excite this bond, and then they probe this vibration. And from this, they can deduce something about the velocity of the energy transfer process here. So again, you cannot really think about these systems as weakly coupled to your molecule. Obviously, this weak coupling approximation doesn't hold here. In other experiments, this side group was larger, so you can maybe associate the temperature to that. So you can try to translate these pictures. But again, it's not going to be a weak coupling limit. So what do we actually observe in our calculations? Yeah, something happened to this. Yeah, so this is a heat and energy current as a function of alpha, okay, alpha half. It's a dimensionless parameter that characterizes strengths of interaction between the subsystem and the environment. And we have different lines, so just focus on two lines. This is for the additive interaction model. If we don't do the polar transformation, energy current goes linearly up. And if we do the polar transformation and therefore convert the model into a multiplicative interaction model, we get this crossover behavior, where eventually the energy current drops as you increase the interaction. And we have seen it in the morning and other presentations. Yeah, and we do believe this result. It was, we can also do some analytic calculations, and it was verified with several other techniques. These two lines in between, actually, we tried to approach the problem using other perturbative techniques. And as you can see, we don't manage to reproduce this actually decay, the actually drop of the energy current, but we get saturation. Yeah, so I think I can move on now to the more interesting application, which is the quantum absorption refrigerator. So this is taken from this very nice paper by Luis Correa, who is probably somewhere here. Yeah. As I've said, there is a very nice review also covering the problem of continuous heat engines, or continuous machines. So again, this is a regular, I don't want to sound critical, but the regular design, which is based on the weak coupling assumption is essential for the operation of this system. You really want every bath to individually couple to a certain transition. You don't want to mess it up. So the cold bath should only couple to this transition, the work reservoir only to this one, and the hot to this one. And there were other designs considered in this paper. So again, in the weak coupling assumption, if you do want to realize an absorption refrigerator, you have to control your system, you have to control the energies, the transitions, and it has to be a weak coupling, coupling has to be weak. What we are going to do, as I've said, we are going to have just a qubit, there is nothing to control, so we are going to control or manipulate our reservoirs and essentially manipulate the spectral functions of the reservoirs. So again, what do they, again, something happened to the symbols. What do they observe in the weak coupling calculation? So this is, again, the regular weak coupling 3-level absorption refrigerator. And this condition is a condition for the cooling condition. So if you satisfy it, you are going to absorb, you are going to extract energy from the cold bath. So the intuition here, as you can see, is that theta cold, which is this gap, must be small, relative to the total gap. If it's too large, it's very hard to extract energy from the cold bath. So that's the intuition. So this is derived, for this weak coupling model. And as I've said, we are going to consider a qubit, but the qubit is going to couple to the bath in this non-additive, what we call strong coupling manner, realizing cooperative effects. And this is what we are going to derive for the cooling condition. Hopefully you remember from the previous slide, it's just the same. And what we have to enforce is, to get this specific limit, is that the spectral functions of the cold and hot reservoirs are shaped in a certain manner, such that if central frequencies satisfy this relation, we actually don't need to filter the frequencies of the work reservoir, but we do need a component here. And we also need to make sure that there are no high frequency components. But in the extreme limit, let's just, for simplicity, filter all frequencies in this manner. So as you can see, the main observation here is that we can realize what they've had in the 3-level absorption refrigerator in a simpler, 2-level system, but we have to use a strong coupling to realize that. So now a few more details. If you think about the qubit with weak coupling, if it's weakly coupled to the different operators of the bath, obviously you can prove it immediately. You cannot realize the cooling because the reservoirs act independently on the system. So each of them individually is going to send energy to the cold bath. There is no way to cool down a cold bath in this scenario. So, and what we do, we have this multiplicative interaction, and therefore realize this cooperative effect, and now we are able to cool down, to extract energy from the cold bath. So a few technical details. How do we get this result? So this is a method that I had mentioned before, the full counting statistics. We just use it here. This is the population dynamics. And this is the equations that we derive for the energy current coming from the cold bath. We can derive expressions for every current in the system. So it's just the same monster from before. It's a cooperative energy transfer process. If you are in the excited state, some energy goes to the cold bath, some of it goes or comes from the hot one, and the rest is exchanged with the bulk reservoir. I just want to highlight that these are 2 times correlation functions for these specific operators coupled to the system from each bath. And they do satisfy, these functions satisfy the detailed balance with respect to these specific temperatures. However, if you go back to the population dynamics and you look at the rates are, again, these sort of convolutions, but you can see it doesn't satisfy detailed balance with respect to either bath. Yeah, it's already a cooperative multi-bath rate. So unlike the weak coupling approach, here you have to deal with different animals for the population dynamics and for the energy current. So from here, that's a general expression. We can do simulations, but we can also try to derive some analytical results. And indeed, in the extreme limit, where these functions are filtered so as to have a single or very narrow function, single component or narrow functions, you can actually solve it and get what I mentioned before. The cooling window is precisely what you receive for the weak coupling, only that now these are frequencies of the reservoir, characteristic frequencies for the reservoirs rather than energies of the subsystem. Other results that we can get, well, we can study the coefficient of performance, the efficiency. Again, we retrieve previous results. And furthermore, we can actually look at the efficiency at maximum power, and quite interestingly, it's already in the limits that the work temperature is approaching this one. We got half of the Carnot efficiency, which is, yeah, quite interestingly similar to other results. So these are the main results for this extremely filtered case, but obviously you would like just to make sure that this absorption refrigerator is not very fragile. We would like to find out whether it can operate in a broader regime. And we looked indeed first analytically, just again shaping the spectral functions of the different reservoirs. Now instead of delta function, they are squares. And you can do some analytical work and again derive a cooling condition so it can still work, and you can derive again efficiency. Delta is the width of your boxes. Yeah, so we start to convince ourselves that this machine can work beyond the very extreme limit. And again, sorry, all the notation is confused, but all these symbols are confused. This is the expression now. We just do numerical simulations, and we can, again, realize a nice cooling window as a function of the temperature of the hot reservoir in delta, which is the width here. So, yeah, and it was a certain choice. You can play with other choices for the spectral functions of the bath. And the intuition here is that when delta becomes too large, when these functions start to overlap, indeed, you are going to lose the cooling operation because you are going to have leakage. You're going to have processes where the work reservoir hits the other reservoirs, so you get these other processes to dominate.
May I ask you a question about the coefficient of performance?
Yeah.
So in the strong coupling, you have flows from all the baths in all directions. So are you defining the coefficient of performance as of the energy from the work of TW bath? It's
J called, it's extracted energy current over JW, the energy current invested to you from the work.
Energy from the hot bath, not the strong coupling, once you go to the non-additive.
No, we use the J call over JW. So it's whatever is coming to you from the work. Yeah, if you have other suggestions, yeah, we can talk. Yeah. Yeah, I just want to mention that we can also control it. The results I just showed you were actually done for the generate qubit. You can obviously start playing. So my main point is that it's not a fragile design. Maybe this is more interesting. You can come up in a regime where it's not operating as an absorption refrigerator, and now start to change the qubit frequency, and you can actually achieve cooling at a certain regime. So with that, I guess I'm over my time. Yeah?
You have one minute of injury time. Yes.
Okay, so I will, yeah, maybe I will just mention again what are these M functions that we shape. So the model, again, was assuming a multiplicative interaction operator coming from the different bath. And if B is just a regular, something coming from, let's say, Caldera-Leggett model, the displacements of oscillators in the bath, then the 2 times correlation function, we can calculate it, and the Fourier transform is, of course, proportional to the spectral density function of the bath. So if you can shape the spectral density function of your bath, yeah, hopefully you can realize this function. So So yeah, in summary, this whole story was done in the context of full counting statistics. We are interested in method developments, playing with different tools to understand better the strengths and applications of different methods. As I've said, we are trying to make some connections to experiments. And yeah, finally, some predictions from quantum thermodynamics, a strong coupling, and what happens if the reservoir is non-canonical. And with that, I would like to thank my group and collaborators. So Chava Friedman, a graduate student in the group, she showed yesterday a poster on the formalism and the result. And then Anki, he did the calculations on the quantum absorption refrigerator. He's a fourth-year undergrad student. BJ was involved in, furthermore, in the squeezing project, Gernot. And I didn't talk about the work of Jiang Guojiang. Yeah, with that, I would like to thank you.